Good morning and hello everyone. Hope all of you are sound and safe. This is Mukhtavar Nawal, co-head admin events at IEEE, and I welcome you all on the behalf of Team UET Taxila on Artificial Intelligence in Smart Grids webinar. We are highly honored to have Sir Adil Arif on the board as a guest speaker. He is a faculty member at the Department of Electrical Engineering, NED University of Engineering and Technology, a research holder USP-CAS eNUST ASU. His research area include AI for smart grids, optimization, protection and control of inverter-based distributed generation system, machine learning, deep learning and reinforcement learning application in time series analysis of power system. He has also 4 years of teaching and research experience at Power System Protection at Smart Grid Lab USP-CAS eNUST and Machine Learning Lab for Power System Arizona State University. Moreover, 3 years of industrial experience at Schneider Electric Pakistan, FFPL Power Company Limited, and Power Tech Research Company Germany. Thank you so much for your time, sir. Before moving forward, let me tell you that it is a 40 to 45-minute session and last 20 minutes are reserved for your queries. If you guys have any query or question, you can type that in the chat box. Now, I guess without any further delay, I should hand over the screen to our worthy guest speaker, Sir Adil Arif. Over to you, sir. The platform is all yours.
Assalamu alaikum everyone. I'm visible and my screen is also visible. Yeah, so am I visible? Just to affirm that, and I'm audible as well.
Yes, sir, you're audible.
Right, so let's start. Welcome everyone to the short webinar series of artificial intelligence for smart grid systems. And let's start this presentation with a beautiful quote of Friedrich Nietzsche, who once said that he who has a why to live for can be almost anyhow. And this is very true about when you describe your journey in terms of your whys and hows, so you make a clear understanding of your life. And I personally think that the vice versa is also possible, that he who has a how to live for can be almost any why as well. So the whys and hows decides usually the times when why you take any decision in your life and why you opted for interdisciplinary field in artificial intelligence and power system analysis and smart grids. So let's just start with why it all started, right? So let me tell about a little bit of storytelling of what happened back in my days, which inspired me to have this experience in 2 interdisciplinary areas. So I worked for 2 of the amazing companies, and I have amazing experience there, which was Schneider Electric and Fauci Fertilizer in Qasim Limited in 2017. So this was the picture of the beautiful power plant there. And I was working there in 2017 in the commissioning project. And what inspired me was there were some excitation control system for generators. And a lot of them used to have a very decent control systems that always had multiple layers of protections. And if I could show you the control system, generic control system diagrams, this was actually the control system implemented there. This was Basler's 250 DEX, and this was the control system diagram for that particular generator excitation system. And it was a very sophisticated kind of machine, and I was like very fascinated when because I was just a mid-career person or an entry-level graduate who was on the job, and I was really inspired to work through these machines. And I was really excited that I am working on these sophisticated machines and high performance machines. But when I was passing through this phase of commissioning, I literally had some sort of things that made me realize that these machines are not capable enough, because they usually fail many times because of, if you can see the power system, the control system diagrams, they are fed to be effectively working on the laid principles, or you can say in a manner which they are trained to work on. And when the situations are odds and things are not likely to as they are designed for, so they frequently fail, despite that they are very sophisticated and high level computation machines and very expensive piece of machine, they fail. So this was my experience with dex 250, which was a very good machine for excitation control system, and which inspired me that despite if we have a very sophisticated control system that is designed for any situation like that, there is a high tendency that we can fail for it, and we need a tremendous amount of intelligence to cope up with real life and real situations. And this static, or you can say the dynamic, static and dynamic control systems are not sufficient enough to describe any practical situation and are not ready to cope for that. So what inspired me was, how about if you could make these small elements, maybe the generator excitation relays and the generator protection control systems and the electrical protection systems, not based on a control hierarchy, but rather an intelligent hierarchy, maybe some intelligent learnable algorithm can be plotted inside these relay features so that we can come up with something that learns by itself, and we are not always there to regulate a mathematical framework for that. So that was the basic fundamental idea that inspired me to learn artificial intelligence in power system protection area and in generation and control protection theory. And what I did was what everyone does in the industry and in the engineering sector. I used Excel. So I tried to plot the values of excitation voltages, protection voltages, stated earth fault currents, whatever the thing and whatever the protections I was working on. So I plotted on Excel, Excel sheets, and I try to forecast the value so that I can get an equal insight of how they are behaving and what is actually the pattern, because sometimes we generalize the pattern to be linear but they are not linear, and sometimes we generalize to be non-linear but they are sort of unpredictable, or you can say stochastic signals, and sometimes they are undeterministic signals. So it's very difficult to model something using Excel sheets, and it also varies location to location, or every particular situation. Things are not exactly able to be modeled in that way. So then my initial approach when I try to model, or you can say forecast the values of parameters on Excel, soon failed because I realized that this Excel is a good tool, but yeah, usually, but you can't. It's not a mathematical manipulation based software. You cannot make a high level computation on Excel. Maybe in future we are seeing a lot of good changes in Excel, so maybe it's possible that in next 5 6 years we would be applying deep learning and machine learning on Excel, because there are some of the formats there is still I guess linear regression and non-linear regression are still there, but the advanced computational algorithms are not there. But there is a high possibility that we might see very amazing features in Excel in the future. So, but at that time in 2017, it wasn't there. So I had to learn a bit of programming and Python and a lot of other languages. And I worked on specific areas of deep learning and reinforcement learning to have my goals achieved. So this was basically the inspiration of mine, how I started working with these intelligent system and intelligent theory in an application to power system analysis, smart grids. Now let's talk about what is actually data analytics and artificial intelligence philosophy for those who are not much familiar, because I think it's a very infield and most of us are somehow have some knowledge of it, and most of I expect there are people out there who are watching this and who have some profiles in it, have some experience in that. So this is for those who don't know actually about what is a data analytics theory. So let's just quickly recall the basic concept of how a data analytics based or intelligent system are different from traditional systems or numerical system relays. So it's quite simple. Usually in data analytics theory, what happened is that you feed a system an experience, or you can say a data, additional experience or a data to a system. And on the basis of that data, um, your controller or your learning program, by using that past experience, uh, try to learn through that experience, and it develops a mechanism for its analytical process by that experience or that data. Like for example, there can be a lot of parameters, what inputs you are giving to it, and by continuously observing like the particular inputs you are applying there, they usually develop a trend there or an analytical process to predict those data, or you can say amalgamate some manipulations there. So once you have trained that particular control system on that piece of data set, then you can always test the analytical performance of the system by subjecting it to a test data. And whenever you give a test data, you have two particular outputs there. That is the results. That means the forecast you are about to have, that what value of that particular parameters occur at time t equals to t plus 1, right? And for the quality of results, right? So how reliable this process is working, it means either it's the data set you have provided or the additional experience you have provided to the control system is it sufficient to have a quality result. So we also have to have a metric to evaluate our results. So there are two important perspectives when we talk about control system designed on a data analytics theory. So the first part is actually the result itself, and the second part is the how do we evaluate the results. So whenever we are taking out any research in any domain of on data analytics theory, so we have to talk about both aspects, that in what quality we are producing that results, and what are those results. So this is basically the theory for data analytics, and this is how we continuously predict our variables, and have maybe sometimes forecasting, and sometimes we have detection theorems, and sometimes, yeah. So we will see in future what application sites we have. So this was the general concept, and then we have some particular areas in artificial intelligence and data analytics theory. Number one is the classical artificial intelligence, which is based on 1990s theory, and you can find amazing lectures on MIT about in artificial intelligence, classical artificial intelligence there. So I usually learn it from there. And there's then again statistical machine learning, then deep learning, which includes neuron-based learnings, and then there is a reinforcement. There's reinforcement learning, which is actually the agent-based learning, and the adversarial learning, which is actually generative methods and discriminative methods-based learning. So these are basically the subtypes or subgroups of data analytics field, and they're particularly different from each other, and particularly sophisticated in each of the developing area. So if you're interested, you can like always search for these terms, and you can learn where these terms are, where these fields are relevant to the applications. For example, like if I have to play a game against some opponent, like for example, AlphaGo was a software, or you can say an algorithm that played chess against the best human player. And whenever there's such type of gameplay theory is enforced to any subject, so the reinforcement learning algorithms are more relevant than other. Whenever we have to have a modeling a non-linear pattern or non-linear forecast of any variable, then deep learning variables are more important. Sometimes machine learning variables or statistical machine PCA SVMs are quite and other than that, deep learning and advisory learning are also quite popular in image recognition and image manipulations. So we have already seen the outrage and you can say the popularity in the deep fake images. So those are actually based on the advisorial. So whenever we are coming to the manipulation of images or so sort of things and extrapolation of 3D objects, so these deep learning and advisory learning are became more relevant. So this is just the general idea of how the application can decide which area you want to work in. So in future, if you want to, like, yeah, but most of the time that we are applying any theory, so most of the time we start with time series analysis because in engineering usually we have one physical parameters going against time. Of course, so usually we are restricted to time domain analysis and yes. So that's the very interesting part. So usually our perspective or engineering perspective usually lies in a generic way in a time series analysis, and there are a lot of quick resources there for time series analysis, and that's the best part about data analytics, which makes it very suitable for engineering applications. So this is just the machine learning subdivisions versus supervised learning. Just this was an interesting slide, but I won't be discussing in detail because it's a subject in itself. What is supervised learning, unsupervised learning, and semi-supervised or reinforcement learning. So there are a lot of the point of displaying this image was that there are a lot of, even if you talk about one of the type of statistical learning or data analytics field, that's a machine learning. So there are still very subdivisions and a lot of algorithms working in that subdomain. So you have to be very careful in what application, what algorithm, and what approaches you are applying, and that's all much about it. Because the appropriate selection of algorithm on approach would decide how effective your algorithm is working. So yes, why we need an intelligent power systems or smart grids? Because we already have smart grids, so why we need further smartness? So you see, the term smart grid is quite abstract, and if you see in the literature, because, yeah, if you have studied smart grid systems, so smart grids are not restricted to some of the basic outlines because they are generations. Like we had smart grid generation 1, smart grid generation 2, and I think we are operating on smart grid generation 5. It is AI based smart grid generation. So before that, uh, what smart grid generations we have do not have intelligence. So they were like mostly, if one of you, most of you have studied that smart grid generations were most likely to be based on indexes and indices. So what we were doing in the past was that we were finding out the indices of voltages and currents and total harmonic distortions to predict the performance or the smartness of the system or that characterize the performance of the system. But now those indices are not much relevant and not a clear metric to define the performance of the system, and we need more sophisticated algorithms and more sophisticated evaluation parameters for those. So why we need intelligent systems in smart grids? Number one is inefficiency to control the techniques, especially for distributed generation. So what is distributed generation? Yeah, it's a concept fairly applies to the microgrids. In the smart grid generations, now we are highly emphasizing on microgrid implementations on the distribution end side. And once you have implemented the distributed generation on the throughout the network, the values of current through the systems and value of voltages are quite unpredictable, and that creates the problem because if you are taking a common generation source and taking that power to the load or the distribution side. So there is only unidirectional current flow from the power source to the load. But when you have a generation source split over all of the distribution network on the generation side, main utility side, and the distribution side, so it creates a chaos of the direction of current. So there are a lot of currents coming from power source to the generation, to the distribution, and distribution to another distribution, and distribution to the generation. So that creates a lot of problem in the control system, because most of the control system, for example, let's say reiteration overcurrent relay is based on the direction of current. So usually those traditional protection would fail under such circumstances, and we can't rely on just the direction of current to pick up an overcurrent relay in such situations. So we will be requiring smart solutions, intelligent solutions in smart grids. Other than that, since there are a lot of unpredictability in such systems, we need computational requirements for multi-array models. Of course, we can't build you can say an NVIDIA processor in the relays, because it's not possible to deploy that amount of processing towards whole of the system, because there are a lot of relays deployed. So we need a system which is optimizable and learnable, so that we might not require that much computation from each end. Then another problem area why we need smart grids is inefficient estimation in dynamic problems, because system dynamics are quite a characteristic of system. We are moving towards low inertial systems, because the generators and dynamos are obsoleting itself, and we are moving towards inverter-based systems, um, including the wind turbines and solar panels, and all the rest of the renewables. So we are like moving towards the low inertial system, where there is no mechanical or alternative to mechanical systems involved there. So the system dynamics are problem there, because you won't be able to detect a frequency surge, because there is not a mechanical rotor attached back to any generator, because there is no generator. That's the point. Plus, then we have a poor selectivity and fault detection. I already discussed this one, that how faults have have a poor selectivity, because the direction of currents are in chaos. And then we can talk about power quality optimization and separate the segregation of economy with performance. So this is a very key area, that whenever we talk about any protection schemes and any control schemes, we talk about how efficient we have made the system, or how optimized we have made the system, but we never talk about the cost of maloperating a protection. Let's say if a protection doesn't operate, so it has a cost associated with not operating, or malfunctioning, or misoperating, or maybe false detection. Maybe false detection has also cost. So yeah, we can also incorporate that amount of perspective of monetization of those faults, or the monetary aspects attached to the fault detection as well. This aspect is also not incorporated right now, and I think this is a fairly uh, related thing to power system protection. That every fault has a consequence, and every fault has a economic perspective. So when a protection scheme is designed on a system, so it should look around the economic perspective, that is it worth it to, let's say, shut down a generator to have that economy boost in the final output, or you can say the optimization. So, and this was a specific case by case application area which I demonstrated here. But if you see on each of the level, on a general level, we can say in any engineering solution, what intelligent smart solution requires to control, to compute, to estimate, to detect, to classify, to optimize. So these six principles holds in a general way. So whatever the six things the application sites I demonstrated here, works in every of the six mentioned on the right. That means for every of the application, I have to control, to compute, to estimate, to detect, and classify, and optimize. So these are the application areas which apply to all the six. And by by having such huge amount of area that requires so much control, so maybe let's say 6 by 6, there are 36 different domains here right now, just by looking on in six different domains. So that creates a huge room for intelligent systems and smart grids. Then I'll discuss a little bit about developing areas in AI-based smart grids. So there, as I said, there is forecasting events, maybe energy forecasting, load forecasting, demand forecasting, maybe. And second area is market research. We are also using AI in market research and technological forecast how many switchgears and transformers are required each year by industry or by country or by voltage level. We can segregate and we can estimate how much uh, particular equipment would be required in the next year. So by it's a huge field if market research recently developed, and I think there is a fair uh, for AI application there. Then there comes motivation. Electricity market. So for several markets, we must teach uh, most relevant to reinforcement. Some pretty developed systems, which includes reinforcement systems, not deep reinforcement systems, traditional 1990 system, which were based on static agents and fixed agents. So electricity market concepts are already in there, and it's a very dynamic field. I see in Pakistan, I think policy, electric markets, and a lot of scope. And my supervisor, Dr. Kashraf, was already electricity markets. He is a lot of projects on in that case. And it comes with demand response and transactive energy and preventive maintenance and planning. Plus, one thing I think is the energy storage. So energy storage is one of the developing areas here. Battery storage or based or hydro-based storage systems are popular, and graphical in Pakistan. I think pumped hydroelectric systems could be a very significant breakthrough, and for that, AI optimization like next level. It, I guess a lot of
Sir, there is an issue with the voice. It's not completely audible.
okay, just yes. Now it's audible now.
Yes, sir.
All right. So let where was I? Yeah, I was talking about the challenging areas, and as I was saying that despite there is a lot of room for research and innovation, there are a lot of challenges, a lot associated with these of the application areas, and which specific to power systems is data limitation. We don't have a lot of data, and that's a tremendous amount of problem in power systems. Because for those who already know that power system machine learning applications or data analytics require a lot of data, right? So in order to have that amount of data, it's not possible that we can retrieve such amount of data from our uh, distribution agencies or generation transmission agencies. And maybe if we are able to have that data for like 10 years is not sufficient enough. So we have to work on like data modeling, maybe, or data augmentation. So these are the fields which would be quite popular in AI, in power systems, in smart grids in future. So the data limitation is very important here, and we have to augment the data. That means we have to replicate the data in, um, or you can say making more data from existing data, hypothetically, right? So we have a equal projection of a higher dimensional data that could be fed into the system, and we have an effective outcome for that, for the training. And number two is explainable AI. That's very important, because when you're talking about engineering solutions, you're not going to tell your boss that, okay, my deep learning says to shut down the generator for 3 days. This is the best case we have. So this is now our industry work. We need reasons to have a decision. So, but AI unfortunately doesn't give you any reasons, for now at least. So what we have to do is we have to design systems of AI that gives us reasons as well for their decisions. So that is the one of the drawback of deep learning. If you apply deep learning in any of the application area, deep learning doesn't give you any information which held inside the black box. So that makes the problem, because there are a lot of application areas of deep learning already developed in power systems and smart grids, but still people are not ready to accept those solutions because they are not capable of giving the reasons. And I think which makes AI and explainable AI most relevant in the field, and reinforcement learning plays a part in such situation of explainable AI. One can Google through it how explainable AI works. So in the additional part, we are uh, considering two case studies, one of my own and one from my colleague who worked with me. Um, so first is actually the hybrid islanding detection. So islanding detection is a protection which I actually. So the purpose of the case study is to show you that how it is applied, right? So it's not just talking about things and leaving you into some places which you are already there. So showing you a little bit direction, people are already working there and how they are working, so that you can also get an equal amount of idea that it's not that difficult, and it's doable. So this was a hybrid islanding detection for inverter-based distributed generation using deep learning. I used autoencoders and unsupervised learning deep learning algorithm to detect islanding, a specific type of loss of main protection, you can say. And I have a paper for that in IEEE open access. The purpose of the research outline was to, number one, the detect the islanding condition whenever the main grid gets off the connected microgrid. So we have to detect it before we lost the system, right? So whenever the main grid is lost, we have to have an information before the system gets out of control. That's the islanding detection part. And I use a generative and discriminative trust strategy. So it's like two AI systems uh, fighting each other and improving each other to have a better performance of the system. So it's like two algorithms of AI, one trying to fake it and one trying to detect it. And that is how the generative strategies or adversarial network systems works on. So this was one of the application of adversarial implications in smart grids. Then the second part includes the calibration of hyperparameters and selectivity of multiple inverters, which was very new for the field. And multiple modes of feature. I use three dependency, or just only three features to detect islanding with a very high efficiency. That was like 20 milliseconds with all of the breaker timings, and which was I think the least amount I have seen in the literature. Then I have a very efficient online and offline validation schemes that not only that was showing the statistical significance of the result, that the problem that I already talked about, that the decision I'm taking must be statistically justified to the human. So I had an offline validation scheme for my operation of detection. So these were the particular systems I applied, because since it was a hybrid system, so I applied active methods along with that. Maybe you won't be familiar with that, but just don't worry about that. And so I implemented active frequency drift in the inverter control. So I changed the inverter control a little bit, and I deployed an active method as well as a passive detection method. And I simulated for all of the power mismatch cases, and let's show you the result. This was actually the process flow diagram. So you start from a value, initialize some values, create a disturbance in the system to somehow an IEEE 154 system model, which is a standard system for islanding detection. And going through that, you have two loops which works independently. One is the main loop, which works on the rate of change of frequency. Another loop is working on the principle of phase angles. So they are both validating each other in the case that if one detects and one does not, so it gives you a clear instruction that something is fishy. And if both of them are operating that, and then I have a control logic to operate that, and that signifies that our detection algorithm is quite so sophisticated. So this was the training example. So on my data set, when I trained my algorithm on the data set IEEE 1547, so this was the, on the very left top was the training curve, or you can say the exponential decaying component of the curve. So the error was greatly minimized, right? So the performance of the system was fairly good. And the left bottom shows the active frequency drift. Maybe you won't be familiar with that, so leave it. And the middle part shows that the red of the zone, if you can see the very center diagram on the red, it shows the traditional operating times. So it's quite high. If you see, it's like 2 seconds, right, for the traditional relays. And the blue one shows the very flat surface, shows the my detection time for the proposed strategy, which was like 20 millisecond or even less than that, demonstrated in the graph below. So that shows a high level of you can say performance compared to the traditional existing strategies. So AI was like devastated here, devastating. You can say the tremendous amount of significant amount of progress was recorded, right? And you can see on the very right side that we have a detection algorithm, and whenever it recognizes the islanding condition, so it creates a patch there to identify that we have a islanding condition there. Finally, so these were the confusion metrics, which shows the high significance of that our system do not fails on most of the condition, except for the conditions which were extreme conditions, highly extreme conditions, and that were tunable to some subject. And it records to be a very high efficiency of value of false detection, low values of false detection and true positive detections. And the right hand side curve shows the segregation of other anomalies with the islanding detection. The blue one shows the islanding detection, and rest were the other phenomena. So we can say that we were fairly able to distinguish between both of them, and that was our target. All right, so what we have now. So we have a lot of techniques here, traditional techniques, which were also deep learning based, and I've compared those techniques with my paper. And this was the performance measures that I have a dependability index of 99%, security index of 99.5%, and F1 score of 0.991%, which shows like a very, very highly dependable and secure strategy of island detection using AI. So in that case, it's an explainable AI. We can say that we have a very high statistical significance of the results, right? This is how in application, any application area you apply AI. So once you apply it, you have to justify it by your statistical results. These are some of the applications expected from this research, that there are low cost solutions for self-sustaining smart grids, And also we know that we are heading towards vehicle to grid impacts in the system. So this would be a very innovative strategy in counterparting that. And then the intelligent power system management, failure cost optimization, and definitely gameplay based power system, that every power system is in the liberal market is working for a benefit or a cost analysis. So they try to compete each other with the low cost and high performance scenario. So that's going to be very interesting area. Second application, quickly wrapping up with, is my colleague Shazad's work in battery management system and battery monitoring system. So what he does was he so this was the basic outline of the project, in which he calculated the state of charge of batteries, and he used to predict that state of charge, because usually for batteries the problem is the health of battery is usually very difficult to predict, and the only parameter that can predict it is SOC, that is the state of charge. In the traditional literature, the state of charge is formulated in a formula which actually characterizes the formula or equation for SOC, but truly does not represent what the equation says. So we need a intelligent system that forecasts our state of charge. So we need forecasting algorithm here. So for the lithium-ion batteries, he picked an application for a NASA batteries data set. So he collaborated with NASA's team, and get the data set for the three of the battery systems, and which were lithium-ion batteries, and he applied forecasting based or neural network. I think he applied, if I'm not wrong, he applied uh, deep learning based system. I think real layer based deep learning systems, and these were the four parameters which he take into account, like load current profile, terminal voltage, temperature. He used these four parameters and number of discharge curves. So he used these parameters for as learning parameters, and he predicted SOC, or the state of charge, as output. And this was the process that he processed through data cleaning process and A point calculation, features extraction, SOH, and finally then to SOC. So this is how he mapped all of the values of the features. F1, F2, F3 here represents features, and we have a prediction, and then we have an estimation for our SOC. And these were the results that he made, a very clear and very beautiful results of pseudo-linear regions. And by using those pseudo-linear regions, he forecasted the values of SOC on every plane, and then he finally, for each of the battery, maybe, oh, there are 3 and 3, 6 batteries. So he did the experiment for 6 batteries, and he evaluated accuracies for each of them by forecasting algorithm. And these were the application areas expected from the research. Of course, there are a lot of scope of batteries when we are talking about electric vehicles coming there, and we are also using about to be using like battery designs for grid system application and portable electronics, maybe, and cell phones. There is a lot of application. So this would be a very good metric to calculate the health of the battery in the current situation and forecast the state of charge for that. So this was it for it now, and yeah, I'll be happy to answer any questions if they are.
Thank you so much, sir, for the very informative webinar. And now we'll be moving towards our Q&A session, and all of you are directed to type your question in the chat box, or if you want to connect directly to the speaker, you can raise your hand too. So we are having a question in the chat box, and Mr. Moiz Ahmed is asking, the energy sector worldwide faces growing challenges relating to rising demand efficiency, changing supply and demand patterns. Can we consider involving AI and smart grids to overcome these deficiencies?
Of course, in a sense that energy systems are also developing industries, but the problem, it is highly intentional to first know about what application side you're working on, right? So let's say if we say that for in current energy systems, we have multiple modes of generation. Let's say we have wind turbines, solar panels, and so and maybe say biomass, and we have traditional power systems. So when we amalgamate all of these, we have integration issues. So to have incorporated uh, our smart grid must be that intelligent enough to recognize the behavior of every type of generation and merge it in the system in such a way that they don't mess. Definitely, it's going to play a very important part, and transactive energy is what the field which I already discussed in there. It's an application side for such innovation and optimization, because every nature of the energy, let's say if we talk about the uh, let's say hydropower, so it's basically the baseline for an average power system, and for let's say nuclear, it's also a baseline. So the total, if we have a system for a country which includes the uh, hydropower plus the nuclear power, you sum that up. This is your baseline power. This is the fixed power you will always get. Solar and wind, you get on and off. Sometimes you have lighting conditions and irradiance conditions. So you have your solar panel working on peak, and sometimes you have wind, so your wind turbines would work, but not definitely. So that's the variable part. Sometimes there is a quick reinforcement part which is actually the coal-based or gas-based generation. So you see there are a lot of dynamics of the types of production, types of generation we have. So we have to optimize our performance by characterizing the type of generation, and which is very important if we allow AI to pop in and have managed this thing for us, right? Yeah, it's a great site.
Thank you, sir. We are having another question in the chat box, and Miss Suman is asking, electrical engineers and power engineers are mostly working on hardware side or control systems, so how can they shift their career towards AI, MI, and analytics side? Further asking, use of Python, R, and other visualization tools are already taking time in this field, and mostly such tools are never introduced in bachelor level. What is your suggestion for that?
Of course, if you have to adopt AI, then you have to go for Python, of course. Maybe not R, but at least you should be able to equip yourself with Python, at least Python, because there are a lot of libraries which you can't find in anywhere else, which are already there in Python, especially like, for example, TensorFlows, and, and there are a lot of repositories which are already there. So it would definitely give you an edge there. So it's recommended. But yes, for the hardware side, which you told that the most of the control systems are hardware based design. So of course it's no problem, because you see the modern hardware, if you see, is not a microcontroller which you are working on. It's a, you can see it's an FPGA based system. An FPGA is a reprogrammable system. So if we can reprogram a system, why can't we program it with an AI based algorithm? So we already have an FPGA based system in our smart grid lab at USPKSE NUST, which we are working on to deploy an AI-based system in FPGA. But the problem with FPGA application is it does not have a GPU, and if you don't have a GPU with an AI, so it's as bad as a traditional system. So we are back in the 90s problem. So now what we will be moving on, the electrical engineers, electronics engineer, and mechatronics engineer will be more working on dedicated FPGAs. So what that dedicated FPGA would be working, that it would have a GPU built inside um, as desirable for the application where we are applying. So we have to have a graphical processing unit that complies with the learning process, and we'll be using maybe Python or Python scripts, or even if you see the MATLAB is 2020 and 2019 have a lot of features in AI if you can directly use them from there. So maybe you can burn those MATLAB or Python theorems or algorithms in the FPGAs, and you can use it as a plug and play device. Another alternative can be, why to use a hardware if you already have a laptop? So every laptop you can plug in a GPU-based laptop with a system, maybe distribution system, and that laptop could work as a protection device. So that's also one of the very innovative strategy. Why to go for a very so if I tell you that the two Dex 250 which I showed in you in the first slide, it was like $10,000 cost, and we implemented like six of them in three generators. So that cost like $60,000 for something that won't work. Why would you waste that? So it in such situation, it in my personal opinion, I think it's better to find a good laptop with high GPU and use that laptop as a protection unit rather buying a very dedicated FPGA for a thing that might not work. So even if it won't work, in the case of laptop, you can change the algorithm and try some other thing.
Thank you so much, sir. We are having another question. Faisal is asking, sir, obviously AI/ML is very important in modern era, but to learn this, it's really a headache that it really take a lot of time. And about AI/ML, there is no such content or subject in bachelor's. So can you guide us and about it and the work on it at bachelor level along with our bachelor level concepts?
Right. So I think this is really astonishing for me to hear from you that there is no available material on AI. I think there is no other material available other than AI on internet. So there is AI everywhere. Google is offering AI solutions, AI courses. IBM is offering a lot of courses. Coursera is full of AI-based courses. Udemy is full of AI courses. So yeah, but apart from that, it's totally right that AI is a deep field, and it requires a lot of patience. So yeah, I think it's worth it if you want to work in research for power systems. But it's not that difficult if you are good at mathematics, and if you are an engineer. I expect all of the engineers to be mathematically very brilliant students. So I think it won't be any difficult for engineering students, at least. And uh, maybe if I wanted to guide you, let's start with the first course. Should be the Coursera Machine Learning Introduction to Machine Learning by Andrew NG. So you can start there because it requires minimal amount of programming there. Just you can use a MATLAB programs there to help you out through understanding the basic concepts of machine learning. Then you can finally gradually move on to other courses from deep learning, and so you can make a fairly basic skill set in AI. And I know that it's going to take time, but once you have the basic skill set and you have the basic understanding how it's working, and you are able to program things and make things work, you will find a lot of resources available. You don't have to find a program that you will encode whole of the tensor flows in them, because we already have a TensorFlow library. You just have to import that library in Python. So it's that fairly easy. But you have to put forward the first initial steps to have a basic understanding of them at least. Use that sort of sorry, use that sort of libraries. But plus, more than that, once you have the basic skill set, the more I think you can learn is by applying on the application side. So pick an application side and try to learn AI by applying into the side. So that's what I have done. Because when I started my programming with deep learning and autoencoders, I think I barely had any, I don't have any actually idea about how these deep learning generative methods can work. I already have some backgrounds of a lot of machine learning I was doing before, and very sophisticated algorithms I was working on, but not this one. So, but I discovered all of the features and all of the problems. I resolved the problems. Meanwhile, the process I was working on a practical problem. So this is how you work, and you gather the basic fundamentals, have some practice, hands-on experience, and then you work on some particular systems and you learn. This is how you work things.
Thank you, sir. A fellow is asking, can you recommend some topics or projects for bachelor students in this particular stream?
So of course, you can always find projects on Kaggle, right? So Kaggle is a website for data sets. You have a lot of data sets and competition for there. So they will ask you to take the data set, and there is a competition that requires you to formulate an algorithm that so it gives you a lot of tasks there. But I think if you don't have any background in AI, so it's going to be difficult for you to go there and compete with others. But of course, it's a very good resource for gathering your data sets, because to learn AI, you need to have a data set on which you can play with. And so you can get your initial data sets from Kaggle, Kaggle, Kaggle. So you can go there and download data sets. Plus, you can always go for the basic programs on Coursera. Introduction to Machine Learning, Andrew Ng, highly recommended. And then you can go for Michigan State University courses, some of the in data analytics and data engineering, a very good specialization if you want to acquire yourself with such skill set. And another specialization I would recommend would be deep learning.ai's specialization on Coursera. And I think there are a lot of other, but I don't want to route you toward paid options. Let it be, start with some free work, free courses, and then you can figure out some other advanced courses in deep reinforcement learning. And but that's another level. So yeah, you can always start with these basic fundamentals.
Thank you so much, sir. As we are, sir, already short of time, there'll be just a last question by my side. And sir, as you have been a part of a very well-known 4G fertilizer bin Qasim Limited company, and it's very famous for supplying energy to K Electric too. So, can we have a few words from you about the experience, about your experience there relating to today's topic?
Sorry, can you repeat exactly? I'm not getting what's the point of KE and FFBL.
No, sir, your experience in FFBL company, and how can you relate that to today's topic?
Yeah, as I already told you that because these industries don't work on innovation, and unfortunately, our power systems and private industries are usually not centric toward research. They are just acquiring things which are sold in the international markets. They just buy. They are just consumers. They buy things, they plug things, and they make it work. So there's a high need for uh, high potential for entrepreneurs to pop in and give some solutions that are even better than international solutions, which they are acquiring. And I think that's going to be the game changer for the country, when you have your own protection schemes working on the system and you are continuously improving those systems. So same hold for 4G fertilizer, same hold for RobDuff, same hold for K Electric. So all of these systems are very sophisticated and good systems. And for example, let's say Angro and all of the other utility systems, they're very good systems, but the problem is they are totally relying on uh, international products. Maybe but they're not curious enough to create their own customized products as per their applications, and that's the problem. There's the problem when they are interlinked with some of the catastrophes. They are unable to match the situation, and they can't handle it because they have no design parameters and control. So I think it's fairly uh, a good idea if someone of you can come up with a entrepreneurial idea in developing AI-based systems analysis, or maybe solution services. Even if you see the maintenance and preventive maintenance side, this is also a huge domain for protection and AI-based systems here. So you don't have to always open the rotor and check out everything is fine. you have to have some AI-based feature that tells you the rotor is working fine without opening it. So there are a lot of applications if one is like subjected to solve solutions.
Thank you. So now, as we are done, it's time to wrap up this amazing webinar. Thank you so much, Sir Adi, for honoring us with your presence. We are highly obliged. I further thank all the attendees who have attended this inspiring webinar. Hope you guys learned a lot throughout the session. Hope we all stay blessed and positive. Take care. Allah Hafiz. And thank you so much, sir, again.
Yeah, my pleasure. Thank you.